After studying this model, you shall be able to know the relations between reducible and irreducible representations, learn how to reduce the reducible representation into irreducible representation, work out the reduction of reducible representation of various point group, and then you can verify your results so obtained. In earlier module, we have learned the statements about great orthogonality theorem and the rules derived from these statements. The rules so derived are quite simple and can be used to find relations between reducible and irreducible representation. These rules were used to find the characters for irreducible representation of D3 point group. Whether the representation is reducible or not can be checked with the application of the rules derived from great orthogonality theorem. In this module, we will learn more about applications of great orthogonality theorem. Let us now learn a simple method for reducing the reducible representation. Making use of the rules about irreducible representation derived from great orthogonality theorem, following general equation can be derived. This equation 1 says AI is equal to 1 upon H summation NR chi R, that is summation sum over all classes, where H is the order of the group to which irreducible representation belongs, NR the number of operations in a class, chi R character of operation R in reducible representation, and chi R the is equal to character for operation R in ith irreducible representation, that is tau I. Equation 1 can be used to find out, number 1, whether in a reducible representation there is ith irreducible representation, whether there is a tau I or not. Second, if tau I is there in the reducible representation, how many times it is present into reducible representation. Equation now, which we have stated above, can now be used to reduce the reducible representation. For this, we will take few examples. Before using equation 1, let us use a direct inspection method for finding irreducible representation for very simple molecules. That is, if we take direct inspection technique, we take a C3 point group for which characters for reducible representation are given, and we have to find out whether there are A or E representation in it or not, and if it is there, how many times these are there. The character table for C3, under E we have 1, 2 and 3. Under C3 we have 1, -1 and 0. C3 2, 1, -1 and 0. That is, I have to reduce, say I have tau reducible 3, 0, 0, and I want to reduce it to irreducible representation. Now, if I simply add A and E together, that is A plus E, we get the character 3, 0, 0, which is the same as tau reducible. That is, which is the same as shown over here. A1 is 1, 1, 1, E is equal to 2 minus 1 minus 1. Therefore, tau reducible is equal to A1 plus E is equal to 3, 0, 0. Therefore, tau reducible is equal to A plus E. Now, let us take another simple example of C2V point group, and the character table of C2V point group is well known. It has force symmetry operation E C to Z, sigma V x z, sigma y z. Now now let us take tau reducible, the characters for which are 3, 1, 3 and 1. And I just want to reduce this to irreducible representation A1, A2, B1 and B2. Now, if I simply add 2A1 plus B1, that is, take the irreducible representation A1 2 times plus B1, I get the characters 3, 1, 3, 1, which is the same as tau reducible character. That is, just by direct inspection for simple molecules, just by looking the characters of irreducible representation, I can reduce the reducible representation. As given over here, 2A1 characters are 2, 2, 2, 2 and B1 character is 1, minus 1, 1, minus 1, and therefore, tau reducible is 2A1 plus B1 is equal to 3, 1, 3, 1. In complicated molecule, this type of inspection method is not easy and process becomes more and more difficult, and we cannot make use of direct method. Now, we will making use of equation 1, we can reduce any reducible representation of a finite group, and we will now look up this in the further examples. Let us take D3 point group. In the table of the D3 characters for TF and TG, reducible representations are given, and I want to reduce TF, tau F and tau Z into irreducible representations belonging to D3 point group. And I just label these irreducible representation of D3 point group as tau 1, tau 2, tau 3. That is, these are the three irreducible representation of D3 point group. So, my aim will be now to reduce TF and TG reducible representation into these irreducible representations. Now, let us take the character table. Let us take the table in which TF has the character for reducible representation as E is equal to 5, C3 is equal to 2 and C3 is equal to minus 1. And I want to now reduce this tau F into tau 1, tau 2 and tau 3. Now, let us make use of the equation as discussed earlier, that is equation 1. Value of H over here is sum of all symmetry operations in the point group, that is 1 plus 2 plus 3 is equal to 6. And let us take the equation 1 and let us try to find out AI. Here AI is tau 1, that is how many times tau 1 repeats. H is the order of the group, that is 1 by 6, and within bracket we take now sum over all classes. NR gives the number of operation in the class. It is here 1, then chi are the character of reducible representation for particular operation. Here in the first is 5. So, like this 1 into 5 into 1 plus 2 into 2 into 1 plus 3 into minus 1 into 1. That is, we have to take 1 by 6 within bracket number of operation into the class into the character for irreducible representation for operation R, and then the character of ith irreducible representation for that operation. So, like this we have 1 by 6 is equal into 5 plus 4 minus 3, that is 6 by 6 is equal to 1. Thus, tau 1 is present one time into tau F. Now, let us find out tau 2. Tau 2 again we will make use of the equation number 1, which is 1 by 6 within bracket 1 into 5 into 1 plus 2 into 2 into 1 plus 3 into minus 1 into minus 1, and the result is 1 by 6, 5 plus 4 plus 3, that is 12 by 6 is equal to 2, that is tau 2 appears 2 times in TF. Similarly, tau 3 is given as tau 3 is equal to 1 by 6 within bracket 1 into 5 into 2 plus 2 into 2 into minus 1 plus 3 into minus 1 into 0, that is 1 by 6, 10 minus 4 plus 0, 6 by 6, that is tau 3 is present only once in tau f. The whole result can be written as tau f is equal to tau 1, direct product 2 tau 2 and then tau 3. This can be verified by adding the character of these tau 1, tau 2, tau 3 in the given table below. Just see D3 we have written in the first column tau 1, tau 2, tau 2, tau 3, and then we have the tau f. Under E we have 1, 1, 1, 2. If I add these together it is equal to 5. Under C3 we have 1, 1, 1 minus 1. It is, if it is added together it is 2. Under C3 it is 1, minus 1, minus 1, 0, minus 1. If they are added together it is minus 1. Thus tau f is equal to tau 1, 2 tau 2 and 2 and tau 3. Now let us reduce the reducible representation tau z again into tau 1, tau 2 and tau 3. After making use of the equation 1 and following the procedure as I have taken in the case of tau f, we can find out tau 1 is equal to 1 by 6 within bracket 1 into 7 into 1 plus 2 into 1 into 1 plus 3 into minus 3 into 1 is equal to 1 by 6, 7 plus 2 plus 9, that is 1 by 6, 9 minus 9 is equal to 0. 1 is equal to 1 by 6 within bracket 1 into 7 into 1 plus 2 into 1 into 1 plus 3 into minus 3 into 1, that is 1 by 6 is equal to 7 plus 2 minus 9, 1 by 6, 9 minus 9, 0. There is no tau 1 into tau z. Tau 2, 1 by 6, 1 into 7 into 1 plus 2 into 1 into 1, 3 into minus 3 into minus 1, that is 1 by 6, 7 plus 2 plus 9, 18 by 6, that is 3. That is tau 2 repeats 3 times into tau z. Tau 3, 1 by 6, 1 into 7 into 2, 2 into 1 into minus 1, 3 into minus 3 into 0 is equal to 1 by 6, 14 minus 2 plus 0, that is 1 by 6 into 12 is equal to 2. Tau 3 repeats 2 times. Therefore, tau z is equal to 3 tau 2 and 2 tau 3. Thus, for Tz, all irreducible representation with the character can be written in the table given below, like this. D3 point group, characters for T2, T2, T2 3 times, tau 3 2 times. If we write it down, then we have the sum tau z is equal to 3 tau 2 plus 2 tau 3. If we add together, we get the character 7, 1 minus 3. Thus, column addition gives the character of tau z reducible representation. That is, by using this equation 1, we can reduce the reducible representation of any finite point group. Let us take the example of C3V point group. Character table without last column is given below, where H is the order of the group is 1 plus 2 plus 3, that is 6. And in this character table, we have the symmetry operation E, 2C3, that is Z, that is the C3 axis along the Z, 3 sigma V. And we have the irreducible representations in this point group as A1, A2 and A. And character for this A1 is 1, 1, 1, for A2 1, 1, minus 1, for E 2 minus 1 and 0. Now we have tau reducible, the character for which is 4, 1, minus 2. And I want to reduce this tau reducible 4, 1, minus 2 into these A1, A2 and E. Let us use equation 1 and reduce tau reducible to A1, A2 and E. A1 is 1 by 6 within bracket 1, 4, 1 plus 2 into 1 into 1 plus 3 into minus 2 into 1, that is, it is 0 by 6, that is 0. No A1 is there into its tau reducible. A2 is equal to 1 by 6, 1 into 4 into 1, 2 into 1 into 1 plus 3 into minus 1 into minus 2, that is 12 by 6, 2. That is, A2 repeats 2 times in this reducible representation. Let us now find out how many times E is there. E is equal to 1 by 6 within bracket 1 into 4 into 2 plus 2 into 1 into minus 1, 3 into minus 2 into 0, that is 6 by 6 is 1. Therefore, E repeats only 1 time. That is, if we take total irreducible representation into reducible representation, we have tau reducible as 2A2 plus A. We can verify this result by adding the character of A2 and E together. As the column addition gives the character of tau reducible irreducible representation. That is, under C2V, we are having A2, A2 because A2 repeats 2 times plus E. And I add the character for this. Under E, we have 1, 1 and 2, that is 4. Under C3, we have 1, 1 minus 1, that is equal to 1. And under sigma V, we have minus 1, minus 1, 0, minus 2. That is, tau reducible is equal to 2A2 plus E, 4, 1, minus 2. So, this is, we can reduce this in a simple manner. Now, in order to go into more clarification, let us take one more reducible representation of C3V point group and reduce it to the irreducible representation. Again, the order of the group H is equal to 6, and again we have irreducible representation of C3V point group as A1, A2 and E. Character for these are 1, 1 and 1, 1, 1 minus 1, 2 minus 1 and 0. And my tau reducible is 6, 0, 2. And I want to reduce it and try to find out how many times A1 is there and how many times A2 is there and how many times E is there. Let us use equation 1 again. Reduce tau reducible to A1, A2 and E. For A1, we can write out the equation as 1 by 6 within bracket 1 into 6 into 1, 2 into 0 into 1, 3 into 2 into 1, that is 12 by 6, 2. A1 is present 2 times. A2, 1 by 6 within bracket 1 into 6 into 1 plus 2 into 1 into 0, 3 into minus 1 into 2, that is 0 by 6 is equal to 0. That is, there is no A2 present into this reducible representation E. Let us find out how many times E is there. 1 by 6 within bracket 1 into 6 into 2 plus 2 into minus 1 into 0 plus 3 into 2 into 0, that is 12 by 6, 2. That is, here E is present 2 times. Thus, total tau reducible is equal to 2A1 plus 2E. How I can verify this result, whether my reduction is correct or not? We can verify by adding the characters for 2 times A1 plus 2 times E. Thus, column addition gives the character of tau reducible representation. We look the table of C3V. I have written over here A1 2 times, E and E 2 times, and I take the character of E 1 1 2 2, and addition gives me 6. Character for 2C3 1 1 minus 1, that is 0. Character for sigma V 1 1 0 0, that is 2. That is, tau reducible is equal to 2A1 plus 2E, that is 6 0 2. Like this, you can reduce number of reducible representation of finite group. For infinite group C infinity V and D infinity H, this formula does not work because H is equal to infinity. And if we take 1 by H, that is 1 by infinity, for infinite groups there is a different way of decomposing of reducible representation, and it will not be discussed in this module over here. We will take up in some other cases. Now, in this module, we have learned the relations between reducible and irreducible representations, and these relations have been explained with suitable examples. Equation which was derived from great orthogonality theorem has been used to reduce the reducible representation into irreducible representations. Examples from various point groups have been taken into account, and a detailed procedure for the reduction of reducible representation has been explained. Examples which were taken were from C3V, C2V, D3, C3, etc. All these types of examples have been taken. In the beginning, I have also mentioned about direct inspection method. For simplest molecules, this easily works out. I have given the example of C3 point group, and I have taken the example of C2B point group, in which we have seen that just by adding the irreducible representation, you can get the character for reducible representation. All these results which we have obtained can be easily verified. That is, as I told you in the case of C3V, that if we add the irreducible representation which have been obtained by equation 1, we get the character for reducible representation. In this manner, what we find, that is great orthogonality theorem, which gives me equation 1, and this equation 1 can be easily used provided we know what is the order of the group, what is the character of the ith irreducible representation. Simply what we need, we just follow this equation step by step, and then you can get the right result. Now, this equation 1 nowadays has been computerized. You just simply put the values of this A1, A2, A3 like this, that is irreducible characters, and you just simply put down what are the characters of reducible representation under symmetry operations and just click on how many times irreducible representation is there. You can easily get the irreducible representations.